What the heck?
Tagon.
Hello, and welcome to the next video on What the Hectagon. It's been quite a while since I've done a video. I was on vacation in 2 different places, so sorry to all 6 of you that are watching this. Hopefully a certain someone is. I'm repping you, boy. Today we're going to prove the law of sines. So we've done a lot of trigonometry up to this point. It's been kind of tedious in a lot of ways, but essentially we're going to start proving the really neat facts now, the stuff that isn't necessarily so immediately discernible from generalizing to circles and things like that. So here we go. Let's talk about the law of sines. So it's a really simple rule and a very elegant proof. So let's get to it. Alright, so today we are going to prove the law of sines. And this is a law that has to do with, it's a law that you cannot break. It's a fact about triangles and the angles and sides within those triangles. So it's a very simple statement. I'm going to draw it out. So if we have some triangle, any triangle at all, it doesn't have to be a right triangle, it could be literally any triangle. And I'm going to label all of the angles capital A, capital B, and capital C. And then I'm going to label the sides, the lowercase version of those letters, the ones that are across from the angles. So this is little a, this is little b, and this is little c. Okay? So, now that those are labeled, here is the fact. So these 3 angles, of course, add up to 180 degrees, or pi radians inside of the triangle, always. And whatever angles they are, as it turns out, and I will be proving this, if you take the sine of the angle A and divide that by the length of the side little a, you get the same number if you take the sine of B, sine of capital B, and divide it by the little side b. And you get the same thing if you take the sine of capital C and divide it by the side little c. And now this seems rather far-fetched. Like, I mean, how is that possible? For a second, before I prove it, let's just talk about what it means. So, for example, if I knew big B and little b, and I knew big A but not little a, I would be able to solve for little a, because I could simply set this fraction equal to this fraction, and because I have this, this, and this, I can take the sine of the angles that I know. Because I have these 3 numbers, I can solve for the 4th one. So what this fact allows you to do is determine a missing part of the triangle should you know 2 of its angles and 1 of its sides, or 2 of its sides and 1 of its angles. You could always solve for it. When you're solving for the angles, say I didn't know capital A but I did know lowercase a, I would have to solve for the sine of A and then do the inverse function, which is called the inverse sine of both sides, to get A on its own. But the point is, you can solve for a missing part of the triangle should you know 2 of either the angles or the sides, and then 1 of the things that is opposite one of those. So if you know those things, you can solve for another part. And so in theory, you could solve for all of them. Because once you know 2 angles, you can solve for the 3rd, which means you can take the sine of that 3rd angle and solve for the 3rd side. So now this is, because these are fractions that are equal to each other, we could invert every side, and an equivalent statement would be that little a over the sine of A is equal to little b over the sine of big B, which is equal to little c over the sine of big C. Remember, the big letters are the angles and the little letters are the sides. I guess a 3rd equivalent statement, because we're dividing by the sine of these angles, we could instead say that it's the cosecant of those angles, so we have that little a times 1 over the sine of capital A is the cosecant of capital A, which is equal to little b times the cosecant of big B, which is equal to little c times the cosecant of big C. Okay, so these 3 are equivalent statements, right? Because these fractions are equal to each other, I can reciprocate all 3 of them. It's almost like a 3-sided equality statement, okay? So how are we going to prove this statement? Well, we need to start with a general triangle, right? I just said that this wasn't just for right triangles, and so I should be able to demonstrate that, right? So here's how we're going to do it. I'm going to draw the same triangle 3 times, but each time it's going to be sitting on a different face, right? So We'll call this side A. We'll call this B and this C, which makes that A, that big B, and that big C. And so all we're going to do is find the area of this triangle. Well, we know that we need to do 1/2 base times height to find the area of a triangle. So it's 1/2. So the area I'll call T because I've already used capital and lowercase a, so we'll use big T for the area. Big T is going to be equal to 1/2 times little a. And now we need to find out what the height of the triangle is. Well, we see that we have a right triangle right here, right? And so we could say that we want the height of this triangle, right? So it's going to be, we know that the sine of big C is going to be the opposite side, or the height that we want, divided by b, right? Opposite over hypotenuse. So that means this is going to be equal to the height that we want, which I'll call h, divided by little b. So to solve for the height, we simply have to multiply the b over, right? So we get that the height of the triangle is equal to little b times the sine of capital C. So the area of this triangle is 1/2 times little a times little b times the sine of capital C, right? Now, there's another way I can draw this triangle. I could draw it laying down on B, right? So it would look like this. How will this be drawn? Like that, kind of. They might not be exactly the same triangle, but we're pretending they're the same triangle. So this is A now, and this is C, and this is big C, and this will be A, and this will be B, right? Capital B, capital A. So now this is the new height of the triangle, right? So this is little c right here. This is the height of the triangle. We have a right triangle on the outside, right? This angle is angle A. And what we're going to do is we're going to find the area of the triangle. So these are the same triangles, right, in theory. And so these areas will have to be equal to each other, correct? Right? Since these are the same triangle, I may be finding in a different numerical way, but they have to be the same. So what are we going to do? We're going to have 1/2 times the base B. And what do we have here? What is this height? Well, it's going to be, we know that the sine of A is going to be the opposite side divided by C. The height is, so the sine of A is going to be the height of the triangle divided by C. And in much the same way that we got the height here, we're simply going to multiply the little c to the other side, and you'll see that the height of the triangle is just little c times the sine of A. Okay? So little c times the sine of A. Right? So, but these two things must be equivalent, right? Because they're the area of the same triangle. They represent the area of the same triangle. And so we're going to draw a third triangle. Do I have room? I guess I could do it down here. And we're going to draw it on sitting on the face little c, right? We did little a, we did little b, both as the base. Now we're going to do the base as with c. And so we simply need to find the area of the triangle one more time. So I'm going to draw it on the base c. So we have the base C, and I'll just move that over a little bit. So this will be C, little c, this will be the angle big C, this will be little b, this will be capital B, this will be little a, this will be big A, right? So we want to find the height of the triangle again. This creates another right angle, and so the areas again will be the same because these are all the same triangle, and we get 1/2 times the base little c, and now we know that the sine of B is going to be equal to the height divided by the hypotenuse little a, which means that the height of the triangle is going to be little a times the sine of capital B, just like in the other two cases. So we get little a times the sine of capital B. Now what I'm going to do is I'm going to erase all the triangles, and we're going to take a look at this set of equalities that we have here. So I'm going to erase this. Okay, so what do we know? We know that the area of the triangle T can be represented in all three of these ways, using the three sides, little a, little b, little c, and the three angles, big A, big B, and big C. Now, what I'm going to do is I'm simply going to multiply all of them by a constant, right? So if they're all equal already, multiplying everything by the same number will keep them equal, right? So this is the area of the triangle, and what I'm going to do is I'm going to multiply everything by 2 divided by ABC. Now that may seem a little weird, but watch what happens. So I multiply everything by 2 divided by little a, little b, little c. Okay? Multiply everything by 2 divided by little a, little b, little c. Multiply by 2 divided by little a, little b, little c. And finally, multiply by 2 and divide by little a, little b, and little c. Now this number is 2 times the area divided by the product of the side lengths. I don't know what that number represents, but the point is we're about to get a lot of nice cancellations, because 2 divided by 2 is just 1, so those go away. A divided by a goes away. B divided by b goes away. Same thing with the 2 and 1/2 here, same thing with the b's there, same thing with the c is there, and same thing with the 2's here, same thing with the a's here, and same thing with the c's here. And we are left with the exact relationship that we wanted to find out, that the sine of capital A divided by little a is equal to the sine of capital B divided by little b is equal to the sine of capital C divided by little c. And these are all equal to some constant, right? The area of the triangle is constant, the length of each side is constant, 2 is a constant, so 2 times the area divided by the product of a, b, and c is what all of these numbers equal, but the point is that they are equal to each other, not necessarily that they equal some particular number, this number right here, whatever this is. It's that these all three equal each other, so we don't really care about that. We just care that all three of these things are equal, and that right there is our law of sines. So we're going to use this in the next video to prove a very, very interesting fact about triangles called the Angle Bisector Theorem. Alright, so thank you very much for watching. I'll see you in the next video.